next to each other, and how that differs from when the road is further apart, etc. And then moving on to the ensemble approach. So here, we asked ourselves, we identified a couple ways that players generally play Catan. Some people will go for the largest army, different settlements. There's many different ways that you could play. Similar to how in any kind of war game you could play defensive, offensive. There's many different strategies that you could play that we've bucketed. So we wanted to see if we could take a big model and then train it to not pick individual actions, but to pick the overall strategy. Because then maybe there's something that we can learn about how to play the best strategy in this type of scenario. And here, these are the opponents. So this is random is the easy, and the value function is the medium, which is actually what we used for the ensemble model. We wanted to compare it against the difficult model, which is the alpha beta pruning. So we have easy, medium, and difficult. So that brings me to the results here. So this is with that first hypothesis, the FNN versus GNN. So I'll explain how to read that. The top row is the kind of the old state, the FNN, and then the bottom is what we're testing. And here with a 4-player free-for-all, the baseline that we want to exceed is 25%. If a model performs over 25%, for example, here you can see both models on the random achieved above 97%, so that means in a game of 1v3, it's winning over 97% of the time. And then value function, you can see that they performed about the same. They performed better than the value function, but about the same as each other. And then here we notice a slight improvement with the alpha beta. So the highest complexity of model, the GNN model performs slightly better. So our hypothesis there is that by understanding the relationship between the roads and between the nodes and the edges, it allowed it to get a little bump up. But we have, I'll mention in a bit when we get to the limitations as to why we think that that's not necessarily a much greater difference. And then here, with submodel sampling, so you can see with the first row and the second row, it performs much better when it's able to identify and pick different tactics as opposed to the actual final decision. And it's performing above 25% on the value function, but still not quite there with the highest complexity model. And then here, this is that varied curriculum. So this was our best model. Again, the models perform very similarly at the random and the value function, but then on that highest level of complexity, we see a jump from 19.5% to 22.7%. So there, we saw that as a result of introducing different models, even ones that are lower complexity, just giving some kind of new variety for the agent to learn from, that improves its results in how it's training. So to summarize these results, so first with that GNN formulation and that methodology, Catan is a very simple version of a war game. But that formulation can be extended for much bigger war games that have different types of units, different types of paths. You can create a whole graph representation that can be quite crucial to making sure you preserve that relational information. And then also that submodel approach, I'll hit on the explainability a bit more in a second. But there, it's quite promising for being able to explain everything. When you have tactics that are abstracted and put into their own bucket, you can understand better what the model is doing as opposed to the model outputting one of 1,000 possible actions and you not necessarily understanding why it picked that. And then also the expansion of varied curriculum research, that ability for a model to improve by seeing variety. And then here, some limitations. So one thing with war games is that they're quite complex. So a lot of the times, these simulations utilize a lot of different CPU, SQL queries, and so for example, Civilization, a similar hex-based game, has many, many different queries that it's constantly running, and it's very difficult to utilize the GPU to train on that data. So that's something that we noticed with Catan, much simpler game, but as this, the state of this research continues, it's important that these simulations are effective for using the GPU. Otherwise, it'll take exceedingly long time for training of a reinforcement learning agent. Then also GNN oversmoothing. So this was something that we found with Catan. Since Catan, although it changes over time, the robber moves and different things change in the game, most war games will have much more of those non-stationary dynamics. Over time, the map will flood. Over time, the map will completely change. And so that's where we expect to see the biggest gains in using a GNN, because the GNN allows you to change and adapt to an indeterminate level of nodes and edges. As long as you have the computation, adding another or removing a section of the map or adding a whole new section of the map, the model will still be able to learn. Whereas that's very difficult and at times impossible to be done with a traditional feed-forward neural network. And then also one thing with AI still struggles a lot with cooperation and negotiation. So we think for the future state, for that to improve, there needs to be work done specifically and not just modeling the state representation, but figuring out how can we give information about negotiation that enables the AI to understand more and to do better. So here, I'll talk about the submodels as nested agents. So what could you put as a submodel? We used the value function players, the medium difficulty bot that we changed and changed for different hyperparameters to go for different strategies. But really anything can be used as a submodel. You could train a specific reinforcement learning agent just for one part of the game to be a submodel. So you can have a parent model select from really any type of heuristic or any type of reinforcement learning agent that you'd like. And that helps a lot with explainability, because previously, with a big black box that's outputting different actions, it's difficult to integrate that into a decision support system or to do much else with it aside from play with it. But having submodels that are geared towards different tactics of the game, you could build in decision support systems and dashboards that show you, in this scenario, we tend to go offensive 97% of the time, or we tend to go defensive. This is actionable insight that can be used to understand how an effective AI agent is thinking about the game and not just the final action that it's returning. And then finally, with agentic AI, by creating these tactics, these submodels, and bringing them into independent, different modularized AI agents, that is agentic AI. So that is a way for taking a big war game, a war game much more complex than Catan, splitting it up into the different sections of the war game. That way, one agent is able to pick from the different agents and understand and actually play the game. Because at the moment, it's much too complex for ChatGPT to play through any of these or any other type of model. So breaking that game into its components, breaking it into its tactics and its strategies is crucial to be able to get results. So now, well, first I want to thank you all again for listening to me, and now I'll open up the floor for questions, and I'll ask Jason and Max to join me. Go ahead. Yeah. So the value function player it's deterministic. It was not trained. It's basically a value function player that's trying to understand the state of the game, broken down into around like 14 hyperparameters. So it would try to understand the amount of victory points that everyone has, the amount of rows that everyone has, and then make a decision of its 1,000 options from that. So we were able to change the hyperparameters and play around with what happens if we put more weight on the victory points? What happens if we put more weight on the roads? So we ran a zero order optimization just to identify, we throw a whole bunch of hyperparameters, can we create different models that are geared towards different strategies? So we created a different selection, one that was the best army-focused one that was the best overall focused one, and we identified and created a model that picked from those. I think that hand was up first. Trading, yes.
It was trading?
Yes.
And when it was playing against other players, were they other similarly trained AI candidates?
Sorry, could you repeat that last part?
Who was it playing against, like in terms of trading?
So when it was, that depends on if it was the self-play or the varied curriculum, but depending on the way that we did the curriculum learning, it would either trade against other random agents, other of itself, or other of the easy, medium, and difficult bots. And so we think that that was a component into how it learned. So a lot of times getting a random trade could kind of help it understand a little bit more about the way trading works. Although clearly it wasn't the best at trading. That was still a significant limitation of the agent. I think that hand.
Did you play with full multiplayer? Did you play like one-on-one or two or three player? And if so, did you notice anything different among like your ensemble agents when you're, if you're prioritizing trade between one player, there's only one other player, but if you're prioritizing trade with like multiple other agents in the game, can you just walk me through that?
Yeah, a great question. So we trained everything and we tested and hypothesized everything on the full 4-player game. But it was possible, and we did end up playing, and we made some kind of test bots. We wanted to see, okay, if we train just on a 1v1 and then we put it into a 1v3, how does it play? But our results are based off of the 4-player free-for-all.
Did you notice any like significant differences when you play like 1v1s versus like 1v3?
From what I noticed qualitatively, playing against the agents that were trained on a 1v1, even 1v1 against the 1v1, the agents that were trained in the 4-player were still better than the one trained on 1v1, just because I think it gave it more opportunity, more experience to learn the game.
I have a question. So you're talking about models learning how to play a game, and it sounds like all opponents or all players are following a set of rules. Have you all ever considered maybe running a model that plays with something like at least one rule breaker to see what the odds of success are?
That's a
How that might apply, like
Ask him what a rule breaker is.
to certain adversaries of the U.S., like might be willing to engage in some ethically questionable acts that we are not willing to. So is there, you think there's something that can be learned there in operating in a
Moving the robber, like being able to.
manner where we can last or defeat
Mhm.
other adversarial plans? I mean, other adversarial enemies, I guess.
Do you want to answer?
So one of the mechanics in Catan is the mechanic known as the robber. So it is an integrated part of the game, but based off certain conditions within the game, you might be able to be a player upon which you can then move the robber to a different game tile from where it is currently. And what the robber does is it robs the resources from those players who have buildings built adjacent to that tile so that they can no longer get the resources associated with it. So it's not necessarily breaking the rules of the game per se, it's already integrated, but it does rob them of the normal rules of if I have building here, I get Y resource, but instead I'm being taken from that. So I guess it is integrated into it, and I know maybe Andres could speak a little bit more to where the model would decide to put the robber's location. I think that's one way we could answer that.
Yeah, I'll add on to that we didn't model anything rule breaking, but for example, the robber, maybe we could have tried to model an agent that would just move it even though it wasn't supposed to, and maybe that would have been interesting to see, but that's not something that we experimented with. But that's a cool next step. One more question. Okay.
Did you try adding any human interaction into it so the AI is playing against humans? So, I mean, I've seen a lot of weird stuff in Catan.
That's true.
I could beat it. Let's go for 6 or something.
We didn't engage it in any training with any human, but for our testing, we wanted to see. So we all played against it, and then Brian also played against it. So I think Han and I won against it. So in 8 people, did any of you guys win against it?
I
You won?
lost 2 for 3.
You lost 2 for 3. Okay. Yeah. So I think it beat most of us, but some of us that were more familiar with Catan were able to win against it. Great question. No, the map would always change, and then it would just be random starting positions. Yeah. Or like you would be able to pick.